The broadcast is now starting. All attendees are in listen-only mode.
Hello everybody. Let's wait a few more minutes for the latecomers before we start. All right. I think that now we can get started. Others can join in the meantime. So good morning everybody and welcome to this webinar, Tools to Get Urban Energy Planning Right. My name is Martin Strolini and I'll be your moderator for this webinar. I am working for Renovate Europe, which is a European expert group dedicated to eco-innovation. This webinar is organized by the Sinfonia project, where Renovate Europe is responsible for the communication and dissemination of the project results. You can view the recordings of the previous webinars via the links displayed on the screen or by searching for Sinfonia Smart City Talks on YouTube. Registration for our last two upcoming webinars is now open. You will be able to find the registration links on our website. They will also be sent to you in the following days as part of an invitation email. I believe that the majority of you already know Sinfonia quite well, but let me still say a few words about the project before we give floor to our speakers. Sinfonia is a project which started back in 2014 and which is funded by the European Commission under the FP7 program. It is coordinated by RISE. Sinfonia is a very big project with more than 25 partners and 43 million euros in terms of budget, out of which 27 million is provided by the European Commission. As you may know, smart city projects usually bring together so-called lighthouse, or if you prefer, pioneer cities, and early adopter cities, or follower cities, as we also call them. In our case, we have two lighthouse cities, Bolzano and Innsbruck. As part of the project, the two cities have been implementing innovative large-scale energy solutions and measures in terms of energy refurbishment, district heating and cooling, and the electricity grid. The main goals of the project are 40 to 50% primary energy savings and the increase of the share of renewables by 20%. The activities of the pioneer cities have been closely followed by 5 European follower cities, Boras, Paphos, Seville, La Rochelle, and Rosenheim. Those cities follow and get involved in the work of pilot cities such as tool and solution development and validation. Apart from demonstrations, Sinfonia has been developing many tools, 4 of which will be presented to you today. We also have a so-called replication cluster, which is a cluster of 47 cities following a little bit less closely the activities and results of the project and beneficiating from peer-to-peer support provided by Sinfonia. Before we get really started, just a couple of technical remarks. The webinar is being recorded. Both the recording and the PowerPoint presentations will be shared shortly after the webinar. You are in listening only mode, but after each presentation, there will be space for questions. The questions can be either sent in writing to the question box you see or asked orally by clicking on the raise hand button you see on your control panel. You can write your questions or raise hand at any time. They will be answered, or you will be given floor to ask them orally at the end of each presentation. Now please let me present you to our wonderful speakers today. The first one to speak is Aliona Zubarieva, who is a senior researcher at the Institute for Renewable Energy of URAC, the European Academy of Bolzano. She will be followed by Inger Lise Svensson, Director of the Energy and Environmental Systems Analysis Unit at Rice Research Institute of Sweden. Then we'll give the floor to our third speaker, Karine Lafonteloire, Senior Consultant at Dowell. And our last but not the least speaker is Jürgen Schnieders, researcher at Passive House Institute. Each of them has a very interesting story to tell. Without further ado, I'm pleased to give floor to the first speaker, Aliona Zubarieva from URAC, who will speak about the Sinfonia SWOT tool for smart city plans. Aliona, the floor is yours.
Thank you very much, Martin. Thank you for this introduction, and good morning to all participants. I would like to thank you all for joining to see what actually has been done in the project and what could be the possible useful tools that you could use in order to start planning or continue the planning for your cities or regions. So here I would like to present to you a SWOT tool that has been developed. This is an online tool that we aim for the cities to be used in order to help them at the very early stage of the planning for the smart city energy project at the city level. And we advise that this tool should be used also by the city managers, by the engineers, by the energy consultants that are working directly with the municipalities. So the objectives of this presentation would be then to introduce to you the SWOT analysis method. So what is behind the tool, how this tool was being implemented online, and then to show you how actually it works and how you can use it directly for your city. SWOT analysis is normally an acronym, as maybe many of you know, for the strengths, weaknesses, opportunities, and threats. It has been introduced already back in the 60s. For the business sector initially, and now it is widely used for all parts of the sectors that need this type of analysis. It is actually a structured planning method that evaluates the 4 elements mentioned before of the project, of the initiative to be implemented. It involves normally the specification of the objectives for the project, identification of potential relevant internal and external factors that would be favorable or unfavorable to achieve the objectives of the project. Regarding the acronyms or the definitions of the SWOT elements, the strength is the characteristics of the project that give it an advantage over the others. The weaknesses are the characteristics that place this project at the disadvantage relatively to other projects to be implemented. The opportunities are the elements that would then the project could exploit to its advantage, and then the threats that the ones that could cause the trouble in the implementation of the project. So why would you then might find the tool of Sinfonia SWOT useful for your own benefit? Well, first of all, it allows the identification a priori of the strengths and opportunities. So even before you start the implementation of the project, you might want to assess which are the potential strengths and opportunities that project could bring to the city. It allows you the a priori identification of weaknesses and threats, and the possibility to elaborate a risk plan that will then allow you to limit or face in the right way the weaknesses, threats that will be faced during the implementation of the project. And then, of course, it lets you to possibly maximize strengths and opportunities and limit weaknesses and threats. This tool has been developed based on the actual implemented smart city projects or similar projects back in the Concerta initiative, and allowed the analysis of 150 already implemented projects in all the member states of European Union. So we feel comfortable presenting it because this actually brings an empirical data to the evidence. How the SWOT is structured, it is, as I mentioned, an online tool, and later on we will see also the direct link to the tool that you can also find through the Sinfonia project website. It is separated in 5 categories, so we try to assess all the elements of SWOT in terms of behavior, in terms of legislation, what are the policy administration SWOTs, economy and finance, and the technology and implementation of within the project. The tool has 38 questions to which only 3 types of answers are requested, so yes, no, or don't know, so it's quite straightforward. And as an outcome of the tool, we will have you will have printable SWOT matrix that then describes the most important issues for each of the elements of the SWOT. It is, of course, then the task of the user to interpret the results based on the local situation in the city, and on how you need to link the drivers, so strengths and opportunities, and how those can be used to overcome the identified barriers after you completed all the SWOT analysis. So if I would like just to go through with you also with the actual passes that you have to take in order to complete this analysis through the tool. This is a direct link to the SWOT, and once you open this page, what you see is the possibility to start the analysis or to obtain more information about how it has been developed and what it is useful for, and then also the possibility to either sign up if you're not registered, or sign in if you're registered and saved your analysis for later. In the part for the more information in the SWOT tool, you will see the description that I gave you before, and then you will also see the sign up link where you have to insert some basic information in order to receive an access to the analysis itself. So you would need to indicate your email address, your username, password, and then repeat your password, and then you sign up. You will receive the access and the confirmation for the access to your email address, which is looking similar to this. After that, you go back to the tool and you sign in with the credentials that you have inserted and that you received per email. And you're inside the system, so inside the internal analysis, where again, you could choose between different tabs, and one of them is actual SWOT analysis. With starting, and you can create your own analysis right away if you haven't done that before, or you can also continue your own analysis that you have saved but have not finalized in the past. You would need to indicate the name of the city for which you're doing your analysis, and then starting to fill in the questionnaire. As I mentioned, per each category of the questionnaire, for example, in this case, for administration and policy, you will have a set of questions with yes, no, I don't know answers. And you, of course, when you answer these questions, you have to think about the situation that is relevant to your city or to your area. For example, the first question in the section of administration and policy is, has the project received a strong cross-party political commitment? Well, what we have experienced from different smart city projects is that normally the duration of such projects is longer than a mandated political commitment. Therefore, you have to ensure the tools of the right methods in order to be sustainable even after the political mandate has changed within the course of the project or within the course of the implementation of the program, in order to actually have the political commitment for the entire duration of your program or project. So once you have answered all the questions, and those are 38, I remind you, you will receive this type of matrix, which identify a number of drivers and barriers. And then in terms of strengths and weaknesses and opportunities and threats, each of these sets are actually describing in detail what are the potential strengths or weaknesses applied for your territory that you can expect from your smart city project implementation. And this would look like this. So you would use then the opportunities of the project during the interpretation of this matrix to try to overcome the threats that have been identified, and the same with the strengths and weaknesses. You would see that there is a correlation between the potential strengths and existing weaknesses that have been identified during the analysis. So this is a very brief description of what is possible to do with this tool. In case of your major interest, I'm always available to give you more information, but also I would advise you to consult an open deliverable that is published on the website of the Sinfonia project that describes how the analyses have been done, which kind of projects have been analyzed in order to create this SWOT tool. And we are always happy to answer your questions should you have any. Thank you very much.
Thank you very much, Aliona, for this presentation. And if there are any questions, please do not hesitate to ask. You can either write them in the question box or ask them orally by raising hand, so do not hesitate. In the meantime, I might ask a short question. How long has the tool been available on the URAC website?
It's been 3 years now.
2 years, okay. And how many times has it been used since that time?
We have received several requests, and I think around 15 to 20 cities have used it for the analysis.
All right. And do you intend to develop it any further after the end of Sinfonia, or to exploit it somehow differently?
Well, we would like to, exploit it more in the update of the background information. So once, of course, more projects are implemented, there are more learning by doing knowledge that is available. So I would like to integrate that further in the background for the analysis.
All right. And now it's free of charge, so will it remain free of charge even in the future, or?
Yes, yeah. We plan to keep it this way.
All right. So let's wait another minute to see if there's a question, and then we'll give floor to our second speaker, Inga-Lise. I think your presentation was very clear.
Thank you.
Well, I don't see any questions, so let's pass on to the next presentation.
Can you hear me?
Yes, we can hear you.
Good. I will just try to.
Maybe try speak a little bit louder.
Yes.
Yeah,
I'll try that.
now we can see your screen.
Great.
Perfect.
Yeah, so good morning. I was asked to talk a bit about the tool Friendly SAM that has been developed within Sinfonia as well, and how this tool has been used to look at what energy solutions matter at city level in the long run. So we have been looking at analyzing scaling of the solutions in Sinfonia. So at first, what we wanted to do, we had a task to look at the impact on energy and CO2 and cost when scaling the solutions. So we wanted to evaluate and compare the total system cost and CO2 effects when scaling the Sinfonia solutions within the cities of Bolzano and Innsbruck. And we also wanted to compare the solutions in terms of impact on economic performance for different energy price scenarios for 2030 and 2050, which were the years we settled on. And from this, we also wanted to analyze what solutions have the greatest potential and whether there are barriers to the scaling, because it's not always it has the same impact. So what we felt we needed here was an optimization tool. And of course, there are already many different optimization tools, but there was a reason why we wanted to develop our own, and that was mainly that we wanted it to be very transparent, not a black box. We wanted more control of what was inside the tool. It needed to be adapted quite well to these specific cities. So we decided to do our own in this case. And what we developed is called Friendly SAM. And it's not a tool as much as a toolbox. It's an optimization-based toolbox. So you can customize your objective functions or what you want to optimize it on. So it could be cost, and in this case it is. You could also optimize it on CO2 or maybe a combination of things. But it's good to keep in mind with the following presentation here that it's cost that we optimized on. And the core concept is that resources like energy flow between nodes, and within a node, those flows can be processed and altered somehow. And the nodes are predefined archetypes. So, for example, a power plant or a heat production plant. There could be a consumer who has a need for energy, electricity, or heat, or whatever. And if you don't have a predefined archetype, because we have developed quite a few for the Sinfonia project, but they can also be customized by the user. You can code your own and add them to the library in the toolbox. So the structure works like this, that there are clusters that are connected, so which will enable some flexibility in the model. So for example, you can have parts of the model that is modeled quite roughly on the level that we have decided is enough. And then the other parts you can model more in a more detailed manner if that's what you feel you need. So it's flexible in the level of modeling detail. And you can also cluster different parts of the system. So for example, if you want to model different parts of a city inside maybe a district, you have quite few limits to how much energy you can transfer between buildings that are very close to each other, for example. While if you're talking about the whole city, from one end of the city to the other, you might have quite significant transfer limitations, and then you can model that through clustering. And you can have different transfer capabilities between different nodes and clusters. So the positives with this, we think, is that it's easy to work with. It allows the user, which is usually someone at RISE at this point, to focus on the model construction and combine the different archetypes. You can compose your models with them, but you can also create new ones when you need them. But you also have a library of already predefined archetypes. So, and you can have minimal code repetition. And this is all programmed in Python, so this is all a lot of code. It's not a graphic tool. What's important for us is that it's flexible and that it's open source, because that was one of the main reasons we wanted to make our own tool, is to make it open source so we can share it. We of course want to use it ourselves, but the whole point for us is also to make this available for others. So you can find this on GitHub. And you can use it with a number of different solvers for optimization. They're all open source ones that work quite well. And we have complete code transparency. So if we put something there, you can see everything. It's the opposite of a black box. It's also quite flexible how to feed in data. So you can have quite different data sets to feed into the model. This was important for us because it's a complex modeling. When you model the energy system of a whole city, you might have very different data sets. So we don't wanted something that was flexible when it came to the data management. So this is only limited by the user, more or less. And you can find it on this link. I will also have it at the end of the presentation. So we decided to do this in the Sinfonia project, and I will show you an example, which is from Bolzano, where we tried the model. So this is a graphical representation of the model, so to speak. So you can imagine that what's in the light blue bubble here is what's within the system boundary. So for example, we have a heat demand, an electricity demand, which consists of all the buildings and users in Bolzano. The heat demand can be supplied by, for example, district heating or other production. There can also be other type of heat production, which is probably the most common thing. The heat demand can also be altered by, for example, building renovation. So you will change the demand. And the same goes for electricity demand. You can make changes for energy efficiency and change it. And then you can also change the supply. You could expand the district heating system. You could change the production somehow. You could introduce storage. You can introduce solar panels. You can do a lot of different things. And of course, they all have different investment costs and running costs, and in different energy savings, depending on what it is you do. And outside of this system, we also have what's outside of Bolzano. The energy market prices are not only local, they are more, at least European, if not global. So then you can have a lot of different things happening. So if you are scaling the solutions in Sinfonia, for example, the renovation, 10 years into the future or 30 years into the future, there's a lot of unknowns about the prices of energy and what type of energy there will be. So for that, we have used different types of energy market scenarios to model that. So if we look at the system inside, we decided to do it like this, that we have, as I said, there's renovation, there is solar PV, there is the possibility for heat storage, district heating, expansion, and production. And we made 5 different cases. There's a business as usual case, which doesn't mean that you don't do anything. It just means that you do things according to the trend as it looks right now. There's a maximum RES, which is where we have locked the solar PV production to a maximum capacity, saying you do it as much as possible, but everything else is according to trend. You could maximize the district heating expansion and production, where we have maximized the grid expansion and the production, and is optimized based on how large the grid is. So there could also be investments. There's the max retrofits case, where we have scaled the renovation as much as possible, according to what's feasible, according to actors in Bolzano. Of course, it's not to unreasonable levels. And then we have the optimal trade-off, which is the main optimization case, because that's where we let everything be optimized against each other. So you will find an optimal level of each measure. Let's see what that means. So for the energy market scenarios, we used quite 4 different scenarios. We have 2 scenarios that were chosen within Sinfonia to be used, which are primes models, and then we also wanted to just to get an idea of the robustness a bit more about the results. We chose also 2 other types of scenarios, and they are mainly scenarios both of what the energy production looks like globally and what the prices are. So they have different fossil fuel prices. You can see in the curve here that they are varying a bit, and there are also price of CO2, and this also results in price of electricity, for example, both for consumers and for the producers. So we have used all of these scenarios to see how it plays out. Are the results different for different energy prices? They should be. So if we look at the optimized investments for 2030, this is just the complete trade-off. So we optimize everything together. We could see that solar PV was considered a good solution in all cases, while the accumulator was not. The grid expansion is is almost the same in for all the scenarios in this case. But only in the 2 first scenarios were natural gas CHP invested in, and that depends, of course, on the price of natural gas versus electricity price, and of course the combined price of heating the buildings in Bolzano in those scenarios. There were also a large level of renovation in at least 3 of the scenarios, but also quite high in the sustainable development scenario. You can see it's almost hidden here behind the line. When we looked at 2050, we had an even higher level of solar PV, still no accumulator though. And the grid expansion was a bit more different. It was quite high in 2 scenarios and medium, more similar to the 2030 scenario in 2 scenarios. And just as in the 2030, natural gas CHP was chosen for the scenarios with a more beneficial natural gas to electricity ratio, but also diamond CHP. And the renovations are at even higher level in this for 2050. And these are yearly renovations, so it's % of the building stock per year. And 1.5% is considered an accelerated level. In the business as usual case, I think it's 0.5%. So if we look at the system cost, which is what we actually optimized on, it was system cost. We have both 2030 and 2050 in this picture. So this is first the business as usual, so what we are comparing to. You can see that negative system cost here is actually a good thing. So the lower the system cost, the better. So what you can see when we maximize the district heating expansion was that it's somewhat better from the system. It's not a huge benefit, but it's still better than the business as usual. In the renewable scenarios, where we have a lot of solar PV instead, it's somewhat better as well. And as with the retrofit, it's still a little lower than the business as usual. So all of them are playing out fairly well, actually. It's not a huge improvement in the system cost when we are maximizing these things, but it's somewhat lower than for the business as usual case. But when we do them all, we can actually see more of a benefit, especially for the medium and pessimistic, as they're called, scenarios, where we can see a lowered system cost. For 2050, you can see more impact. For the business as usual itself, This very much depends on the prices of energy. And as I said before, business as usual doesn't mean that you don't do anything. It means that you do it according to trend. So you are still doing both renovation and some district heating expansion and some solar PV. It's just not to an accelerated level. In this case, the maximum district heating expansion looks rather similar, or is even perhaps a little worse than the business as usual case, which we could also see later on, well, previously in the 2050 optimization results. The preferred case was not a maximum district heating expansion, but a quite large one. And in this maximum, we have put it maximum. What is looking very good is though the solar PV, which gives very low system cost, which depends on very much on the electricity prices for 2050 in the scenarios. And when it comes to the retrofit, it's better than business as usual, sort of, but it's quite similar. It's not a huge difference here. But the trade-off scenario is looking quite positive, and there you are doing a little bit of everything. You are renovating to a higher level than could be expected. You have a lot of solar PV, and you have expanded your district heating grid to quite a large degree, although not to a maximum degree. If we look at the CO2 emissions, which is of course of large interest here, we are now comparing to the business as usual to make this visible. So it's 0 for the business as usual. And in the district heating case, it's actually when we have expanded the district heating grid to a maximum level and allowed for investment in natural gas CHP, you have an increased CO2 emissions. So that's not so great. Of course, that could be different if you chose to invest in something else, but these were the options that we had discussed and were involved in this model. It's not a huge increase, but there is some increase. The renewable is, on the other hand, showing, as expected, a decrease when you have a large production of solar PV. And the renovation is also showing good results in reducing the CO2 emissions. And the trade-off is sort of showing a combination of all three here, that you have a lot of solar PV production, you have quite a bit of renovation, and the district heating expansion is to a level where you don't perhaps need to increase the CO2 emissions very much, at least in total. For 2050, well, the business as usual is 0 because it's compared to that, but in that case you have still a bit of a higher increase in CO2 emissions from if you have, for example, natural gas CHP. There's an even greater possibility for reducing CO2 emissions through solar PV, and the building renovation shows quite good potential here to reduce CO2 emissions. So the combined effect in the trade-off scenario, where you can do all of it to the extent that which is most profitable, is that you can actually reduce CO2 emissions quite a lot, depending a bit on the scenario, of course, it very much depends on the electricity prices, which show how important that is for the profitability of the investments. So the main conclusions here are, yes, renovations that are done in Sinfonia, they are to renovate to a quite high extent is economically efficient at system level at reducing CO2 emissions, and also from a point of view. But it should be remembered that the investment and the benefit is not always to the same actor. It's especially in the case of social housing, it's the building owner or the municipality need to take a lot of investment, but the whole benefit of reduced energy cost might come to the consumer. This can cause a problem in the profitability of renovating buildings. if not any of the income is coming to the person actually doing the investment. So that's something we'll talk about more in another webinar. We also saw that expanding the district heating grid is economically beneficial, but the emissions could actually increase depending on what heat source is replaced and what heat source is introduced in the system. So from a financial point of view, it's a good idea. We might have to consider what's the option from a CO2 point of view. And the solar PVs looked very good in most scenarios here, at both reducing emissions and from a financial point of view. But there is something to be said about the grid effects, which we did not consider in this analysis. If you have a lot of solar PV production at the same time in the same part of the system, that could cause problems. So there are other investments needed, perhaps, or at least more flexibility in the power grid to make that large expansion possible. Thank you. And as I said before, you can find the Friendly SAM model at GitHub or at this website. And you can also contact me if you have any questions.
Thank you very much, Lisa, for this insightful presentation. Now that we have space for questions, so again, you can ask them in the question box or raise hand and you'll be given floor to ask them orally. Please don't be shy. And there's already one question from Julien Joubert, who's asking, when you consider the total system costs, does it include investment and operational costs?
Yes, it does. They have been periodized per year. So you optimize for 1 year, but you include the investment cost that's allocated to that year and the operation cost, yes.
All right. So then we have a second question. Could the model be used to look into scenarios of greater electric car ownership, for example, additional storage capacity through grid-connected batteries? Do you see any use cases in the context of the current pandemic, e.g. home office work, less travel, etc.?
So for the electric car use, yes, I think that could be used. You could definitely do different scenarios of electricity demand and see how that looks. You could probably combine it with other Python models for grid effects, which are important in that context. As for the pandemic, well, I mean, you can use this model to look at different types of resilience issues, I think, which are part of the crisis problems, I think, to look at how that's impacted. I haven't considered that, but it could be.
We have another question, again from Julien Joubert. How many cities did use this tool? And is it a geographical information system, GIS tool?
It's not a GIS tool, no. We have mostly used it on, I would say, right now, 4 or 5 cities, all in different EU projects. It's first in Sinfonia, we used it for Bolzano, and to some extent to Innsbruck. We had somewhat different data there. We also used it for Gothenburg in another project, and we have used it in other Swedish cities. Yes. And the all early adopter cities as well. Sorry, I forgot about those.
There is Maxim Kultunov who wants to ask a question orally, so I give you the floor, Maxim. Wait a minute. Yeah, here you go. Hello, Maxim.
Hello, do you hear me?
Yeah, we can hear you.
Yeah.
Oh, Thank you very much for a good presentation, first of all. And my question is like, maybe you know something to elaborate about. You mentioned about the solar PV systems that we don't know like about the grid effect. And if I remember right, like I read somewhere in like on the Sinfonia website that there was some another tool elaborated by the researchers about the volume and kind of the places where the solar PVs could be kind of installed in the district in order not to harm the grid. Do you know something about this? Because if I remember, there was something in some tool elaborated like as well like during the Sinfonia project.
Yes, I think there was. I think yes.
I can answer this question because we have in Europe elaborated a so-called PV hosting capacity tool, where that allows you indeed to simulate the placement on the real grid applications of the PV without compromising the stability of the grid.
So like, and maybe, I mean, this is like Friendly SAM, and these two are totally different tools. So like, are there any ways to integrate these two tools, or they're completely different and there is no possibility?
I mean, because Friendly SAM is more looking at the potential on a high level. So we haven't looked at the power grid on a detailed level here at all. But if you look at that level of which is financially beneficial here, you can of course analyze it through the other tool perhaps and combine them and see.
Yeah, to answer your question is that we haven't integrated it yet, but I think it could be an idea for further projects.
I agree.
Thank you for the answer.
You're welcome.
Thank you very much for the question, Maxim. So are there any other questions? Yes, we have one question in writing, so I will just read it out. Was there any consideration of the PV production challenges with respect to the use of some harmful compounds and materials and the danger to humans handling and at end of life?
No, it wasn't. We used the life cycle based emission factors, but that's the only way the life cycle was considered in that way. So no.
Let's wait a little bit more to see if there's some more questions. And do you have any plans to exploit or develop any further the tool after Sinfonia ends, because the project will end quite soon?
Yeah, no, we are definitely developing new archetypes and using it in other contexts. So we are continuing to use it, and we will try to keep the website updated as well with our updates, because we keep it open source also after the project.
Richard Walklin, who asked the previous question, says that it's very important to take into consideration the production challenges with respect to the use of some harmful compounds.
Absolutely, I agree.
So I guess we have no further questions. So I will give floor to our third speaker, Karine Lafonteloire. Karine, the floor is yours.
Can you hear me?
Yes, we can hear you.
Yeah, okay, brilliant. And can you see my screen? Yes?
Yes.
Yes? Okay, brilliant. Fine. Right, so I will now present you what we have done in Sinfonia with a tool that we call CROCUS, which is providing support to the long-term planning of energy efficient renovation at district scale. So my presentation is a bit long, I think, so I will go quickly through it and we can come back to some of the slides if you have any questions. So the objective of CROCUS is to take into account the energy in urban planning, because unfortunately it's not always the case, or at least it's not taken into account in a holistic way. It's a decision support tool that will help to target the district that should be refurbished in priority, and comparing the impact both in terms of energy and economic impact of different long-term refurbishment plans. The objective of the tool is also to bring together different types of data, which for now are too often used in silo, but by different departments of municipalities, and also to find alternatives when data are missing, because there are often data sets that are not available for some municipalities. So the tool can work with the first limited data sets, and it allows to answer the needs of cities that, for example, don't have consumption data at the building scale. So what has been developed in this project? So basically, it's an integration environment that brings together different modules. So one of the modules is Friendly SAM, which was already presented by Ingerlise. Then there is a module called DemoSim, which is really the core of CROCUS, which simulates the energy need at building scale, and which was developed by CSTB, the French Research Center on Buildings. Then there is a prototype of PV potential module, and then a module that brings all this together and calculates different KPIs. So the data we enter to this tool. On one side we have meteorological data, then GIS data on the buildings, climate data, statistics on the population, and the way they use different appliances, for instance, and then data on the district heating network. And all this feeds an online dashboard, which is for now locally hosted, which is not as flexible as we would like. So we tend to use a GIS software instead to have more flexibility in the presentation of the results. Then, depending on what is displayed, there are possibilities to instantiate new simulations or to slightly adjust the renovation plans to do new simulations. So just a few more details on DemoSim, which is a proprietary tool of CSTB. So it generates models of thermal loads at building scale using different physical building parameters, such as the U values, the building footprint, its height, and so it calculates the nominal loads at the time steps of 10 to 30 minutes. It also generates the electrical and thermal loads for those buildings. So the need for heat, for space heating, for instance, but also the electrical need for different types of appliances. So the approach we implement with CROCUS is in 5 steps. So the first step is to collect city data, so data on the buildings themselves, their age, height, if they are residential or commercial, data on district heating, if there is any district heating network, also socioeconomic and statistical data, data on the local energy mix, and data on the long-term energy strategy of the city. We then create the city model, so we identify the different types of districts, within segment the city into the corresponding district, and we enter the data into CROCUS. I will describe all these steps in more detail with some pictures later on. We then calculate the baseline energy consumption at district scale. So we run this simulation describing the existing state with CROCUS. Basically, we first simulate the baseline consumption at building scale, and then we aggregate everything at district scale, so it's easier to see. And then we calibrate using existing information on energy consumption at city or district scale when available. The fourth step is to quantify the impacts of a set of renovation plans. So we define the renovation plans together with the city. We also defined, if it's relevant, different long-term scenarios for external parameters such as energy prices or CO2 prices. And then we run the corresponding simulation in CROCUS. So for now, we simulate 2 levels of renovation, a medium renovation and a deep one. And as I said, we have different scenarios for the evolution of energy prices. The fifth step is to compare then the renovation plans. So we visualize the results on maps and on the diagrams to allow the comparison of key performance indicators, and if needed, we can refine the renovation plans. So this approach and the tool are being tested with 5 Sinfonia cities. First, the 2 pilot cities, Innsbruck and Bolzano, and then 3 early adopter cities, Borås, La Rochelle, and Rosenheim. So we are at different stages of the study with those cities. So today I will present in more detail what we have done with Bolzano and Rosenheim. So the first step, the collection of city data. You have here the example of Rosenheim. So the city of Rosenheim provided us with GIS data, which contains key information on buildings, such as their age, their function, what kind of energies they are using, their height, if they are connected to the district heating or not. And these GIS data sets cover more or less half of the city. So in the end, we are able to include 4,000 buildings in the study. We also got other data, such as energy mix, local primary energy factors, and CO2 emission factors, energy prices, and most importantly, the cost of renovation technology. Then for the other data we need, for that we use other sources of information. For example, for the building performance, so the U values, we used the tabular database to derive U values from the building age. So the second step is the segmentation in districts. So what we call here district is actually rather a building block or an homogeneous set of buildings. So it's not an administrative district, but we look at the urban fabric and we segment it into a homogeneous sets of buildings. So similar age and similar size. So you can see here what has been done again for Rosenheim and Bolzano. For the buildings that are not covered, most of the time it's because it's too mixed, let's say, to be able to define a district, and also for reason of available time, unfortunately. So a few examples of those so-called districts here in Rosenheim. So you can see different district types. For instance, the one at the top, the low-rise, open, modern. So basically, it's a small, it's single family houses mostly, and with a majority built after 2000. We then simulate the baseline energy consumption. So as I said, it's first done at building level and then aggregated at the level of the district. So you can see here the demand for space heating within each district in Rosenheim. The little numbers, it's not the demand, it's the number of the district. So that's for Rosenheim, and we did something similar for Bolzano. The fourth step is to simulate the impact of renovation. So in Rosenheim, we simulated 2 scenarios: the standard refurbishment, which is targeting the energy consumption values that are set by the current regulation on renovation. And the second scenario is an advanced, a very ambitious one. And for this one, we use the U values that have also been used by PHI in their study of the Castellnau district, and I assume this will be presented by Jürgen later on. For Bolzano, we decided to test slightly different scenarios. First, kind of usual shallow refurbishment that only includes roofs and windows, and then an advanced one which targets the latest energy consumption values. So that's the data we get displayed as a bar chart. So on the left for Rosenheim and right for Bolzano. So for the existing state, so it's all for the energy need for space heating, for the existing state, for the standard renovation, and for the advanced one. What I forgot to say is that here, when we mean renovation, it's only the renovation of the envelope. So far, we haven't factored in any retrofitting of the heating system. Right, then we can compare the indicators. So I'm showing here provisional data because we are fine-tuning them for the final report to be delivered to the cities. Here we can compare the payback times obtained at district scales for the 2 levels of renovation in Rosenheim. So as you can see, the payback time are rather long, but it's because we have simulated very ambitious renovation. So it's not unusual to see such a long period. And for Bolzano, as you can see, as we simulated a more shallow refurbishment, the value on the left show a shorter payback time. I would like to put here a slight warning. So I think what's interesting here is whether the relative rather than the absolute values, because, well, it's a simulation, so it's always to be taken with care. So for us, it's more important to use this value to compare different options and compare districts between them than use the absolute values. Also, the payback time that I presented here, I tend to think it provides a rather biased and incomplete picture. It gives a preference to the low-hanging fruits and not to the most energy-efficient measures. So there are other indicators that may be better suited. Also here, our calculation of the payback time only accounts for the financial benefits that are related to energy efficiency. We haven't included here the non-energy benefits, as they are more difficult to monetize, but those co-benefits are really key when defining a building renovation. And so here again, the objective is really to compare options and not to use absolute values. So this being said, the tool also provides other results and indicators, like the energy need for domestic hot water and cooling, and for other electric appliances, primary energy, and greenhouse gas emissions, and also other economic indicators. So then what? So what do we do with those indicators? So for instance, if the payback time is the criteria of selection, then when we look at the results for Rosenheim, we could say, well, then let's go and let's start with building block number 19. So for that one, if we decide to refurbish it completely, the overall investment will be around 3.2 million euros. But other KPIs may be more relevant depending on the city strategy. For instance, the reduction in CO2 emissions or the maximization of energy savings. So we can here use the combination of the payback time and the reduction of CO2 emissions. And from this graph here, it appears that it's those two little districts that are the most interesting. We did something similar for Bolzano too, which put forward those 4 districts here. But again, it's really a matter of the city defining what are the indicators that make more sense. And the selection of districts should also account for the different urban planning strategies that are very dependent on the local context. For instance, some districts may be in an urgent need of a renewal, and it's something we cannot really tell with our tool. And in all cases, stakeholders consultation is key. Once the district is selected, CROCUS is really a first step decision tool, but then a more detailed analysis of the targeted districts needs to be made, for instance, with the tool that will then be presented by Jürgen, the PHI tool, and with energy audits of buildings the refurbishment choices also need to be optimized, and the required investment need to be better estimated. And then, of course, financing needs to be unlocked with the smart financing alternatives, as Lisa said. Then we get all the challenges related to split incentives, who pays and who gets the energy savings might not be the same person. So how do we tackle that? How do we motivate the building owners? But that was the topic of another webinar. Short conclusions. First, on the lessons learned when developing and using CROCUS. So we integrated different modules. In the end, that proved to be much more difficult than expected. The environment is complex. It's in Python, but we have different versions of Python used in those modules. So it made our life very tough. Then data. So for each city, we have different conditions for data collection. Depending on the local regulations, for instance, on data confidentiality, and also the available data sets, GIS tool, and so on. So, which means that with different data coming in, we also get different model outcomes. About the data on building footprint and height in Bolzano, it was really straightforward, thanks to the work that had been performed before by URAC. But in some of the early adopter cities, there was a lot of pre-processing required to clean the data and to make it suitable to be used in CROCUS. And so in all cases, the data pre-processing and post-processing are heavily time-consuming. The next steps, so we have an ongoing work with Bolzano and Rosenheim to validate the results obtained with the simulation and fine-tune the way we present them in the report. We also have to complete the analysis for Innsbruck, La Rochelle, and Borås, and we'll then be able to deliver good practices and recommendations based on the outcomes of all those studies. So thanks for your attention. I don't know if there are any questions.
Thank you very much, Karin, for the presentation. And again, you have some space for questions, so do not hesitate to ask. I might have a short question. Will the tool be somehow available to some potential users in the future?
Yeah, so what we have now, it's a prototype, which is lacking a nice user interface. So it makes it difficult to distribute and share. And for now, it's whether used internally at the well. But we are working with CSTB on defining an exploitation strategy, first for CROCUS as a whole. And also in parallel, CSTB is further developing the DemoSim module. It's embedded into other tools as well. So they might be more commercial application on that side.
Hello.
Does it answer your question, Martinia?
Hello, Martin. Can you hear me?
Yes, we can hear you perfectly. Sorry.
Okay. Yeah, thanks. Julien Joubert, working at Energy Cities. We are part of a project a bit similar, which is called Hot Maps, and URAC is part of it. It's a urban planning tool allowing to do mapping and planning also, and it's a GIS tool mostly dedicated to heating and cooling. So I'm quite interested in your tool. I had 3 questions regarding your tool, just to make sure I well understand. First question is, what is the impact of the DHC energy mix on your calculation, or is that an impact on the results, or because in one of the input modules there is the one on with DHC information?
Yeah, so I haven't presented here the results of what we get with the friendly SAM, but basically all the consumption we simulate at building scale is then fed to friendly SAM, which optimizes the district heating network, so which will be can be interesting information. So basically, it's just that the DEMOSIM information is used to feed friendly SAM. Then apart from that, we also use information on the local mix of energy when we calculate the CO2 emissions and the primary energy. So the local characteristics of the local district heating and cooling network will also have an influence there.
Okay, thank you. And just to be sure, all the modules are needed. The one DEMOSIM, friendly SAM, and the PV potential modules, they are compulsory before starting to use the CROCUS module. No,
it's mostly DEMOSIM. DEMOSIM is really the core.
Okay.
Then the PV one can run independently, but well, for us, the most interesting for now is really the DEMOSIM simulations, because they will allow us to get an assumption of the consumption at the building scale and then district scale.
Okay, and in case you don't have the building level data, you're still able to simulate them.
Well, to simulate the buildings, we need at least their footprint and height and age.
Okay.
And then the tool will simulate their consumption using assumption on their U value.
Okay, right. Thank you very much.
Welcome.
Thank you very much, Julian, for the questions. And there's also Maxim Koltunov who wants to ask a question. So, Maxim, I give you the floor now.
Yes, hello. Thank you again for a nice presentation of such an integrated and complex actually tool. And my question is whether it was kind of the initial aim, like maybe one of the aims of the Sinfonia project, to create such a complex integrated tool for assessing like which district should be chosen and whatever, or it was something born as like during the project activities, like as the integration like of the other tools, and was the idea that like we can create the integrated tool for all other tools in order to assess which district to choose and which outcomes there will be, or it was something that it was planned at the planning of the Sinfonia project stage.
And sorry, I think my connection is a bit poor, and I had difficulties to understand you. So can you repeat your question, please?
Yes, actually, the question was it an initial like aim, like one of the aims of the Sinfonia project to create such a tool as CROCUS, or it was something born during?
No, it was indeed an objective of the project. There was a full work package dedicated to it.
So there was a full package. Okay. Thank you.
Thank you very much, Maxim. And we have one comment from Richard Walklin. He says that I have noticed a key aspect of energy saving is not often mentioned, but offers significant advantages for energy recovery, lowering CO2 and energy use. Any comments appreciated?
Yes, sorry, Martin, definitely I think my connection is very bad. Can you repeat the?
Yes, of course, don't worry. It's a little bit hard, yeah, because everybody's working from home, so the connection can get a little bit tricky. Yeah, Richard said that he has noticed that a key aspect of energy saving is not often mentioned, but offers significant advantages for energy recovery, lowering CO2 and energy use. Any comments? Appreciated.
So that's the indicators we use in CROCUS. So let's say that's the one that are easy to calculate, and that I think makes sense. But I would like again to stress that there are a lot of other co-benefits that should be taken into account when planning a renovation that I quickly touched upon and that were presented in more detail in the previous webinar, including the improvement of comfort, of accessibility, and other co-benefits. I'm not sure I have time to go into detail now, but you wrapped it a very interesting work on this topic.
Yes, definitely. Richard Walken says that he was referring mainly to heat recovery ventilation systems. They could offer significant advantages for energy recovery, lowering CO2 and energy use.
Okay. Well, no, sorry. Yeah. As I said, for now in CROCUS, what we have simulated is mostly the insulation of the envelope. And for now, we haven't simulated any changes to the energy system or any changes made to the ventilation. But this will be done indeed. And I agree it will be important to do it, to have really a more integrated vision of a deep renovation.
Yes. Well, I don't see any further questions, and we are running a little bit late. So, Richard wants to ask the question by speaking, so I give him the floor. So, Richard, you can speak now.
Can you hear me?
Yeah.
Thanks. Good presentation. Thank you. I'm very interested in energy recovery, and I'm involved in mainly the residential market and in New Zealand. And I've been watching this seminar with interest in how it's done on a city and a more larger scale. And there's opportunity here in New Zealand to do that as well. So, but my question was really regarding around the heat recovery ventilation system idea, just because that it is a very good outcome for dollar invested. The energy use that they use to ventilate a building is extremely low, and the returns are extremely high, meaning that it returns comfort, it returns health, it returns cleaning of the air from a CO2 in buildings, as well as getting rid of VOCs and the like. But also it offers this energy reduction from the additional energy that needs to be introduced to the building to keep it comfortable. So I just think that it is a passion of mine, as you can probably tell. However, I can't overestimate the importance of a good quality mechanical ventilation system with heat recovery offers to schemes such as these on larger scales. And the bang for your dollar is extremely good value. And I just wanted to make that comment.
Okay, thank you. Yeah, sorry if I misunderstood your question. That's okay, that's clear.
Thank you very much, Richard, for the comment. Karin, you said that you couldn't understand, right? Yeah, I guess.
Right? Yeah, no, I can understand it.
Okay. Well, if there are no further comments or questions, let's go on to the last presentation. So now please let me give the floor to our last speaker, Jürgen Schnieders from Passive House Institute, who will speak about the districtPH tool for energy balancing at district level. Jürgen, the floor is yours.
Yes, thank you, and hello everybody. I just have to change the screen to view, and we tested that before, but I have to find.
Yeah, now it's perfect.
So this should be the presented version, right?
Yeah, now we can see it perfectly.
This presentation is about districtPH, which is a tool that we developed at PHI, and it is about energy balancing at district level. So we all know that something needs to happen to our CO2 emissions and to our energy systems, that we have to go to renewable energies, to clean energies. And the question is, what is the role of the buildings in between? And that was what we were going to address in developing this tool. So the structure you see here is from the very beginning. In the center, you see what is called, what was called the district tool in the starting phase, and what later got the name districtPH because it's from PHI. We want to model the energy balance of a district, whatever size it may have. So first of all, in a district, there are buildings for which we can do a simple energy balance. We may be lucky and have individual passive house planning package energy balances that could be integrated. But in general, there will be a statistical distribution of different building types, which we are using to model the energy demand of the buildings in the district. And then these buildings have load profiles. So depending on the time of day and on the time of year, we will have different loads for heat, for electricity. There will be grids transmitting this electricity, or maybe also the heating or the cooling. So district heating, district cooling grids may be present. We may have monitored energy consumptions of model refurbishments, and that's indeed an important point, which I will address in the next slide. We wanted to have electrical mobility integrated to see what the effects would be if we get a large number of electric cars in the district, and how this affects the electricity consumption and also the possible use of electricity. Energy production is considered, so PV production, solar thermal, wind energy, biomass, and of course the conventional non-renewable energy production plants. And finally, there's public consumers like street lighting or public transport. The whole thing is one big Excel table, so it is pretty easy to set up, and it allows for a lot of flexibility to add additional auxiliary calculations, additional modules, anything that you would like to know from the energy balance of the district. So first of all, for us, it seemed important to get as accurate an estimate of the heating consumption of the buildings as possible. And what we find when we look into the literature is that there are some apparent weaknesses of the current typical heating energy consumption calculations. So this is one example from Germany showing the calculated heating demand of a number of non-residential buildings here on the horizontal axis, going up to 300, 400 kilowatt hours per square meter per year. And from these buildings, also the actual energy consumption was known. And of course, you would like to get a good agreement of demand and consumption that is of calculated and measured. which would be represented by this angle bisector here. But in reality, we see that particularly for the poorly insulated buildings, we are strongly overestimating our consumption. So the actual consumption is lower than what we have calculated. And that's not only the case in this example. There are about 10 or 20 different results, different comparisons from different sources that all show a similar pattern. Now, on the other hand, we know that for highly insulated buildings, at least for quality assured passive houses, we get a very good agreement of what we are calculating and what is actually consumed in the buildings. This is an example for about 70 passive houses that have been built in the United Kingdom. And we see that they have large differences in the annual space heating demand or in the measured consumption, which is due to different user behavior. But on average, they have a measured space heating consumption of 12.7 kilowatt hours per square meter per year, quite close to the design goal of 15 kilowatt hours. So apparently our calculations are quite okay for the highly insulated buildings, but not so much for the old existing building stock. What could be the reason? From a physical point of view, we would expect that there must be lower temperatures in the buildings because somehow the energy balance must be fulfilled. We do know that we have the heat losses through the building envelope depending on U value and temperature difference. And if the U value is more or less correct, it can only be the temperature difference that results in the lower measured heating consumptions. So what we could derive also from dynamic simulations, assuming that rooms are only heated if there's somebody in the room and that there is a night setback also of the temperature, was the correlation of the heat loss coefficient of the building and the indoor temperature that we should assume for the energy balance calculations. Our results are quite similar to the slide you are seeing here, which is from Institut Wohnen und Umwelt in Darmstadt, already from 2003. And they also assumed that the size of the dwelling units will make a difference, that in a large single-family home or in a very large apartment, it is more likely that some rooms are not heated at all, whereas in a small dwelling unit, if you only have a single room, the fraction of setbacks will be lower. So that was also integrated into that formula, and the whole relationship was integrated into districtPH. Now, how do we calculate that? First of all, we need to get an information about the district, and that's well, usually pretty difficult and time-consuming to get that. What we are suggesting here is to use the tabular and episcope typology that is freely available and relatively well known, I think. We integrated that into the tool so that you can simply say, okay, of the building type 48, we have some 2,500 square meters of living area in our district. And then the respective number of buildings becomes part of the calculation. In addition, of course, it's possible to define your own building types, which will then be calculated. What we are not doing deliberately so far is a GIS data import, because the availability of data is very inhomogeneous. So in some locations you get relatively detailed data. In others, it's just the height of the buildings and nothing else. In any case, manual data processing would be required anyway. And if you want to really get the data from a building in detail, that may easily take you like half a person year or a full year, which is usually not available for practical application. So what do? We take these building types, so not individual buildings, but we are only looking at building types, which can also be, say, an individual supermarket in the district, of course. These building types are connected to power plants, to an electricity grid, to renewable energy production, maybe also to a district heating grid. And then we are calculating the balance in a specific year. Now, one of the major goals in developing this tool was to be able to predict how the energy performance of the district is changing over time, how it can be improved, and how long it will take, depending on your strategy, to reduce the CO2 emissions or primary energy consumption to a certain desired level. So we now calculate the renovation of these buildings. We might change view values of walls or exchange windows or integrate a ventilation heat recovery. Or we might also change the way buildings are provided with heat or domestic hot water or where they get their electricity from. So that would give us year 2 and year 3 and so on, up to 50 years, depending on what you want to consider. And now, if you try to implement that, you get into one major difficulty. And that is that in reality, all the components of the buildings are not always refurbished at the same time. In fact, economically, it only makes sense to insulate your wall if you need to do something to your wall anyway. So if you need scaffolding, if you need a new plaster, then it's the time to also add the insulation, which then is cheap or a cheap add-on to what you are doing anyway. And the same is true for windows. You would replace them once they need to be replaced anyway, and that's the time to install a highly efficient window. So there is a certain, there's not just an unrenovated building and a renovated building. There's all types of different mixtures. And the way we decided to deal with that was that we assign a probability to every refurbishment. So we use one representative of each building type. We calculate its energy consumption, depending on the total floor area of this type, and then we improve the efficiency year by year, depending on the retrofit probabilities. But now this is also a result that is probabilistic. It depends on the actual probability of a certain refurbishment. So we are running that model with different probabilities with different random numbers several times until the average, which is the black line here in the diagram, would converge to sufficient accuracy. So I'd like to show you a few examples too, because of time constraints. Number one is this district, which is located in central Germany. Buildings that have been built in the late 1990s, early millennium. We decided to look at 4 different scenarios. All of them keep the same heating system for simplicity, which is assumed to be gas. And then we looked at the total CO2 emissions and how they develop over time if we follow different refurbishment strategies. So number one would be we are just doing what is required by the building code in Germany. If you are changing something, you need to fulfill certain requirements, maximum U values and so on. That would be the orange line here, which gives a slow reduction of CO2 emissions over 50 years. If we decide that that's too slow, we could try to increase the refurbishment rates. So we do that in the beginning, and in fact, we get lower CO2 emissions quickly, but we might recognize after 10 years that this is quite costly, that we need high subsidies, and if we cut these subsidies after 10 years and let the system carry on running, nothing will happen for a long time, because those buildings where it made the most sense to renovate them economically have been renovated using the subsidies, and then we are just approaching the original orange line in the end. We could also instead use an economic optimum approach. So whenever anything needs to be done, we are doing what we call NRFIT, so basically passive house components, high insulation, triple glazing, highly insulated window frames, ventilation, heat recovery in these buildings. And since the buildings are relatively new, it takes some time until that takes off. But then we get a significant reduction over the decades in the CO2 emissions of the district. And we also can see here the lock-in effects that we get from poor renovations. So if we follow the step of increasing the refurbishment rate, but renovating the buildings only to a medium quality, we are following that yellow path. And then if we decide already here after 10 years that we need better qualities, again, nothing happens because everything has just been renovated, and you will not kick out your newly installed windows, which are just 5 years old, in order to get higher energy efficiency there. So this has long-lasting effects. Even after 50 years, we are still in a situation that is quite worse. So these types of scenarios can be analyzed in districtPH. Usually we are using just 2 typical weeks, one in winter, one in summer, for reasons of performance and calculation time. But in principle, it's also possible to do hourly analyses over the whole year. So we can look at how much PV in yellow is available here, and then how far it can cover the load profile, which is the dotted line, how much wind energy, the blue one, is available, and the whole thing in summer and in winter. In winter, you will find here that we have a lot of orange electricity available, which is electricity from a heat controlled CHP plant, and that's not available in summer because we have less heating demand. We only need a little hot water and the losses of the district heating system. So then we need additional storages, which can also be implemented to cover the remaining gaps here. Another example, a newly built district in Berlin. So this is not about renovation. They had about 30,000 square meters of living area to be built here. And the questions to be addressed were which efficiency levels do we best aim at for the buildings? Should we use gas? Should we use district heating, which is available here? Should we use electricity? What is the influence of electric vehicles? And also, what is the ecological impact? And what is the cost of the different variants? Altogether, we calculated about 15 different variants. The most important ones are shown here. So on the left-hand side, we have now here shown the primary energy renewable demand. PER is something that tells you in a totally renewable energy system, how much electricity needs to be produced to cover your energy needs. So if you have to convert your PV electricity to hydrogen, then to methane, and then back to electricity, you will have a lower or a poorer PER factor and a higher PER demand than if you can use the electricity right away. So number one is the standard solution, moderate insulation and district heating. And then if we improve the insulation, if we add heat pumps, if we add drain water heat recovery to the domestic hot water system, then we get lower PER demands. And also the cost calculation, interestingly, showed us that the investment for district heating is lower. So these bars show us the total investment per square meter and year. Well, not the total, the additional one for those components that were of interest here. And then we are able to sell some PV electricity, and we get some subsidies if we are improving the insulation level, so that the most cost-efficient solution in that case was use good insulation on a passive house level, use a heat pump instead of district heating for the space heating, have direct electric heating for domestic hot water, and use the drain water heat recovery to reduce the electricity demand for hot water production. It may also be interesting to see that if we assume that all the parking lots in the district, 230 altogether, have electric cars which are charged as soon as people get home, what the results will be. The design team was particularly interested in how they could possibly use their PV electricity by themselves, because then they get a better economic results than if they sell it to the grid. So the load profile is again the dotted line. And here in the afternoon, we assumed that most people come home with their cars and connect them for charging. And in wintertime, we are able to just consume all the electricity that is produced by the PV system on the roof in the district. Nothing that needs to be stored, nothing that cannot be sold to the inhabitants there. In summer, it's different. We have a lot of excess electricity, which we can partly put into a storage, the battery storage we assumed here, with 1.5 megawatt hours. And then the storage is full, and the rest of the electricity needs to be exported. And during the nighttime, the storage is then providing most of the electricity that is used in the district. Okay, so that's basically it. districtPH, as I said, is an Excel table. We are running some beta tests, somebody else, not we ourselves at PHI, is applying the tool to different tasks. As I have shown you, we had first applications, and we intend to have the tool available in September at the 24th International Passive House Conference. We also developed training courses, because it turned out in the first tests and from the first feedback that modeling a district with all the different components that are involved does require some expertise and some know-how, which should be, that was the feedback we got, provided by a training course. But in addition, there's also a manual available. From a personal point of view, as a developer of the tool, you should also be able to use it just by reading the manual. So, thank you very much.
Thank you very much, Jürgen, for this interesting presentation. We are running a little bit late, but still, if there's one or two questions from the audience. You can ask them now. For the time being, I don't see any. So you said that the tool will be available in September, right? And it will be free of use.
Yes, it is already available now. So we are providing it to individual interested people, like at the cost of promising that they will give us feedback on their experience. We will have to charge a certain fee starting from September when it is really commercially applied and available, because well, Sinfonia was not 100% funding. It was just a support of the work we did.
Okay, thank you. So you want to finalize it by September based on the feedback that you will have received?
Yes, that's the intention.
Sophia Barker is asking a question. Could the tool be used for a small group of buildings, let's say 3 or 4 buildings?
Yes, definitely. In that case, it might make sense to define every building as an individual type. And then you would also get the results for each building type, which then means for each building individually.
Julien Joubert asks, is it an online tool or a software to install?
It is neither. It is just an Excel table, which is running a few macros because we couldn't do it totally without macros with the renovation strategies. So all you need is Excel version 2013 or later, nothing else.
Okay, thank you for your questions. I don't see any further questions for the time being, so I think that we can run to the end because we are a little bit later, and I'm sorry for that. So thank you all for your interesting presentations and questions and for your participation in this webinar. As mentioned at the beginning, this is the 4th chapter in our webinar series. So if you missed the previous ones, I encourage you to catch up on previous episodes, and do not forget to join us on the 13th of May. If you would like to know more about Sinfonia, you can of course go to our website. We will distribute all the presentations in the coming days. A short survey will be sent to you, will appear once this webinar is finished, and it will also be sent to you by email. We would really appreciate if you could answer it, as it helps us improve our webinars and adapt it to your needs. And many thanks again to all the participants and the speakers for their contribution. If you have any further questions, do not hesitate to send them to us by email, and please keep in touch. Goodbye, everybody.
Bye.
Goodbye.